All right, this is the third portion of the 4.1 lecture. This is on compound interest. So previously, uh, we did a compound interest problem, and we had monthly compounding, but we were given an annual interest rate. So what we had to do was we had to solve for a monthly interest rate. However, we can come up with a more generic compound interest formula that prevents us from having to worry about whether I'm given a number of months or quarters, etc. This allows us to very quickly do all of that math. So this has A of t is equal to A times 1 plus R over K to the KT power. Maybe the K in this exponent is difficult to see. That's to the KT power. Here, A of t is the account value or the final value. T is measured in years. A is the starting amount of the account. This is often called the principal. R is some annual percentage rate or nominal rate. And K is the number of compounding periods in 1 year. Let's look at an example of how to use this. If you invest $3,000 in an investment account paying 3% interest compounded quarterly, how much would the account be worth in 10 years? So I'm investing $3,000, so my principal, or my initial value here, is $3,000. My interest rate is 3%, so R is 0.03. This is compounding quarterly, which means 4 times a year, so K is 4. And now, remember this formula was A of t equals A times 1 plus R over K to the KT, right? And we're looking at 10 years. We want to know how much this will be worth in 10 years. So T is 10. If I plug all of this into this formula, A of t is equal to 3,000 times 1 plus 0.03 over 4 to the 4 times 10. And putting this in a calculator, I get $4,045.05. This is how much the account will be worth in 10 years. Moving on to the next example here. A 529 plan is a college savings plan in which a relative can invest money to pay for a child's later college tuition. And the account grows tax-free. If Lily wants to set up a 529 account for her new granddaughter, wants the account to grow $40,000 over 18 years, and believes the account will earn 6% compounded semi-annually, this means twice a year, how much will Lily need to invest in the account now? So I have an interest rate of 6%, right? This interest rate is 6%, so R is 0.06. This is compounded twice a year, so K is 2. I don't know an initial amount. In fact, I know a final amount. I want this to grow to $40,000. So this means actually that A of t is 40,000. And I want this to grow over 18 years. So this means that T is 18. So I suppose A of 18 is 40,000 to be exact. Now if I plug everything in that I know, I have that 40,000, which is A of 18, is equal to A times 1 plus 0.06 divided by 2 to the 2 times 18. This means that 40,000 is equal to A times plugging this stuff into the calculator, I get 2.8983. And solving for A by dividing both sides by this number, I get that A, my initial amount, is $13,801. This is the amount of money that Lily should invest in the account in order to have $40,000 in 18 years. We just have a few more concepts here. Because of compounding throughout the year, with compound interest, the actual increase in a year is more than the annual percentage rate. If $1,000 were invested at 10%, the following table shows the value after 1 year at different compounding frequencies. Notice that as we compound more frequently, that the amount of money increases. This is because with each step, you have more money in your account, right? So for instance, if you're accruing interest daily, then every day you have more money in your account, and the extra money that you have in your account is also accruing interest. If I wanted to compute the annual percentage increase for daily compounding, well, you see from $1,000, there was a $105 increase. So if I take $105.16, well, this is the increase from my amount of $1,000, and I divide this by $1,000, you see that this is I get here 0.10516. This is a 10.516% increase. This quantity is called my annual percentage yield. The annual percentage yield is the actual percent a quantity increases in 1 year. It can be calculated using this formula: 1 plus r over k to the k power minus 1. Let's look at an example of annual percentage yield. Bank A offers an account paying 1.2% compounded quarterly. Bank B offers an account paying 1.1% compounded monthly. Which is offering a better rate? Well, for Bank A, I want to calculate my APY for both of these, my annual percentage yield. For Bank A, this is 1 plus 0.012. That's my percentage rate as a decimal, divided by 4 because it's compounded quarterly, raised to the 4th power because it's compounded quarterly, minus 1. And this gives me uh, 0.012054, which is a 1.2054 percent growth rate. For Bank B, I calculate my APY by doing 1 plus, my rate here is 1.1%, so as a decimal, this is 0.11, divided by compounded monthly, means it compounds 12 times a year, and I subtract 1. This gets me 0.00, or no, 0, sorry, too many zeros, 11056, which is 1.1056%. So Bank A offers the better rate. The more frequent compounding for Bank B isn't good enough to catch up with Bank A's better APR. This means that Bank A is offering a better rate. And our last topic here is this idea of a limit to compounding. So let's examine the value of $1 invested at 100% interest for 1 year. Notice that as my frequency in this table is increasing, that the amount of money in the account is increasing, but once I start to get to daily, and then hourly, and then minutely, and then secondly, that amount of increase is going down, right? They're all 2.71 something, right? You're barely gaining any money at all, especially between compounding per minute and compounding per second, even though per second is 60 times more frequent, right? So there appears to be some kind of upper limit to the amount that the frequency can, how do I phrase this? There appears to be an upper limit to the amount that the frequency can affect the growth rate here, essentially. And there is. This is a number that gets represented with its own letter in the same way that pi does. This number is called E. E is the letter that is used to represent the value that 1 plus 1 over k raised to the k power approaches as k gets really large. And E is used in continuous growth rate. This is what happens as we just let the time the time between compounds become very, very small. So essentially at every single possible instant, we're compounding in continuous growth. So continuous growth will be used for things like chemical reactions, it'll be used for things like population growth, and things like radioactive decay. These things are more or less changing all the time, nonstop, continuously. This is actually a very simple equation. Here, f of x equals a times e to the rx. And e, this is also called Euler's number. This is about, like we saw on the last page, this is about 2.718, This is a very special number, just like pi. And we should have a button on our calculators for this in the same way that we have a button for pi. Let's look at an example of a continuous growth. Radon 222 decays at a continuous rate of 17.3% per day. How much will 100 milligrams of radon 222 decay to in 3 days? Well, we're given a continuous decay rate here, so we're going to use our continuous growth formula. And my R here is going to be negative, since my growth rate is negative, since this is decay. So R is going to be negative 0.173. Then what do I have here? I have that F of 3, this is the amount of radon 222 in 3 days, is equal to, my initial value is 100 times E to the negative 0.173 times 3. And if I plug this into my calculator, I should get about 59.512 milligrams remaining. And one more example. If $1,000 is invested in an account, earning 10% compounded continuously, find the value after 1 year. So my growth rate is 10%, so R is 0.10. We're starting with $1,000, so A is 1,000. So I'm trying to find the interest after, or I'm trying to find the amount of the account after 1 year. So I'm trying to find f of 1, because I'm given an annual interest rate, right? This is 100 times e to the 0.1 times 1. And this is $1,105.17. And this is it for 4.1.